Hey guys, welcome to this video on torque, which is covered in level 2 mechanics. So it was made another slideshow. So first things first, what is torque? So basically, torque is basically the sum of the rotational forces that is acting on something. It's similar to Fnet. So it's Fnet, like I say, is like the forces acting on an object, but instead in this case it's rotational forces. Torque is rotational forces on an object. So I could say that like it's really similar to Fnet. So I could say it's balanced. So if I say the torque net is balanced, that means the sum of all the torques is 0. The unit is Newton meters. Okay, unit for torque is Newton meters Nm. And if I say it's balanced, that means that all the torques are balanced, which means that the clockwise torques and the anti-clockwise torques are equal. That means there will be no rotational acceleration, and the object will remain stationary in terms of the rotational acceleration. If the torques are unbalanced, then it will experience a kind of rotational acceleration in a specific direction that it is unbalanced in. Okay, so like Fnet, you can say, Fnet is, for example, 5 newtons to the right, but for torque, it's more of a rotational force, so you have to think of it more like spinning. So it's not up, down, left, or right. It's more clockwise and anti-clockwise. So there's two directions. It's a clockwise or anti-clockwise, and an example would be 750 Newton meters clockwise. That means there is an unbalanced torque of 750 Newton meters in the clockwise direction. And because there is this unbalanced torque, that means there is also an acceleration in the clockwise direction, the rotational acceleration. Alright, so you don't really know the details, but torque is represented by a Latin symbol, which is tau, and it looks like the one on the Google Doc doesn't look like the actual one. The actual one looks like it looks like a fish hook, and then it's like a fish hook and then a cap. Okay. So the one on the Google Doc doesn't look much like the actual one, but search it up on the web and you should get a good image of. It's like fish hook. Can't really. It's hard to explain. So in level 2 mechanics, every year there's going to be a torque question guaranteed. Okay, and there's always an excellence question in the torque section. So the merit and excellence question normally involve you to have to find the force exerted by a support force. Okay, so basically that's the most common excellence level question. So it's mainly this subtopic mainly based around calculation rather than theory. So there's not that much theory in this topic. There is some theory, but there's not a lot. So alright, so the most common, and I think it's the only formula that you really use, is torque equals to force times the distance. And that assumes that the force and the distance are perpendicular, so they make a 90-degree angle. So for example, if the force is acting downwards, that means the distance must be horizontal, so exactly 90 degrees to 90 degrees to each other. Alright, so another important concept you need to understand is the idea of equilibrium. So this is a very common word you'll come across in the torque section, and what it means is that it's defined as the forces is all balanced. So when I say forces, I mean both the Fnet and the torque net. Okay, so this means that the object is completely stationary or that it is moving at a constant speed. So basically the state of motion isn't moving. So refer back to Newton's first law. Okay, so the state of motion is not changing. For this to happen, like I just said, Fnet must be equal to 0 newtons and torque net must be 0 Newton meters. So for many of these questions, it's basically going to be assuming that the object or whatever you're considering will be in an equilibrium. So basically, that's just saying the sum of the torques on the object is 0 Newton meters. And that's true for like 98%. I can say like 100% of the questions is going to be assuming that it's in equilibrium, but unless it's specified by the question, you can just assume it's in equilibrium. Alright, so it's an important note. It's not really related, but like just an important note I decided to add is like, so if you have considering a weight force of an object, always remember that the weight force always acts in the center of mass. So exactly halfway of the length. So for example, if I had a 5-meter beam, the weight force of the beam would be exactly acting at the 2.5-meter mark, which is halfway of the beam. Alright, so the most common torque questions will look something like this. So there's gonna be some kind of a beam, or like so just, it doesn't really have to be a beam, but like just like a platform, and it's gonna be 1 or 2 supports, and on this beam, or there's gonna be like an object. I'm just drew a person here, so this is gonna be like an object or a person, and there's gonna be 2 supports. Okay, normally it's 2 supports. I just say, but most of the time it's just 2 supports. Okay, so basically what's happening here is that we have our support forces, which is offered by the 2 beams, not 2 beams, the 2 supports. Doesn't have to be beams, like I said. It could be like anything really. It can be like if you're carrying a plate, it could be your fingers. If you're on a bench or something, it could be the table legs. I mean, it just could be anything that's providing the upward force. Okay, and the downward forces are always acted by the objects on the platform and the platform itself. Okay, the platform itself has also a weight force acting down, and that's where the center of mass comes into play. This is just it's really common for them to ask you to label. Okay, so when it comes to labeling, just remember a few things when it comes to labeling. I didn't make a slide on labeling, but when you're drawing the vectors for the forces acting on the object, always remember that the bigger the force, the longer the arrow. Okay, so for example, if the person is here 60 kilograms and the bench here is 100 kilograms, that means the weight force of this bench will be the arrow will be longer than the weight force of the person, and that's because it's larger. Okay, and in terms of drawing support forces, this person here is a lot closer to this left support than the right support, so that also means that there's actually going to be more force. This left support is going to provide more upward force. So once again, this left support is going to have a longer arrow than this right support here. So just a few basic key facts just to remember when labeling. Okay. The size of the arrow does matter. If you wanna achieve the maximum grade, the size of the arrows you have to make sure that's right. Okay. Alright, so we're gonna move into our first example somewhere. So yeah, just 2 support force, and then there's a person exerting a downward force, and yeah, okay. This is example 0. Alright, so a person of mass 50 kilograms stands on a seesaw. The person is 3.5 meters away from the pivot. The 7.8 meter long beam has a mass of 100 kilograms and has a center of mass 0.5 meters away from the pivot. So calculate the torques. So we have our diagram here. Alright, so we have this person and our support force, which is not necessarily support. We just say this is our pivot point. Is going to be this triangle here. Okay. So in terms of calculating the torques, okay, it's basically being able to identify whether the weight force would be clockwise or anti-clockwise. Okay, so we're going to consider this pivot point as like a pivot. So you remember when I said torque equals to force times distance? This distance will just basically be how far is the object from this pivot point. That's what our distance will be. Alright, so now you're looking at this image. Okay, so you see this person's on the left hand side. If you're thinking it's really hard to explain, but just imagine. So right now this person is going down. Just imagine you're on a seesaw, right? If you're on a seesaw and all of a sudden the ground disappears, then okay, that's a bad example. So let's say you're on a seesaw. Okay, so let's say that you have your friend on one side and you have you on this side. Okay, let's say you're heavier than your friend, so that means that your side's going to go down. If your side's going to go down, if it keeps going, let's just say the ground isn't there. If you just keep going, then you'll notice that it actually goes into like a specific direction of motion. Okay, in this case, let's just say there's a person here and nothing over here. So this person is going to make this, let's just say this is not equilibrium. So let's just say this person, this weight force is going to push this down, and this is going to go in that anti-clockwise direction. And so that's how we get our direction, okay? Sorry, it's pretty difficult to explain, if you know what I mean. So, and also we have our center of mass of our beam, okay? That's also in the anti-clockwise direction, okay? So, because it's on the left of the pivot. So if it was on the right of the pivot, if I put an object on the right of the pivot, and if I remove everything on the left and just put something on the right, as you can see, this object's going to push this beam down, and once it goes down, it's just going to move in a clockwise direction. And that's how I get clockwise torque if it's on the right side of the pivot, and if it's on the left side of the pivot, it's going to be an anti-clockwise torque. Alright, so in order to answer this question, okay, we need both a direction and a magnitude. To calculate the magnitude, we just need to use our formula, which is torque equals to force times distance. So we just add the distances here, so 0.5 meters and 3.5 meters, okay? So basically, force times distance, the force refers to the weight force of the object, torque is what we're trying to find, and the distance is the horizontal distance the person is away from the pivot point. So now this becomes pretty simple. So now we have our mass of the person, 50 kilograms, times by the acceleration of gravity, which is 9.8, and we have 3.5 meters away from the pivot, and that is added to the 100 times of 9.8 times the 0.5, which is the mass of the beam, and the distance, which is 0.5. Okay, so the reason we're adding is because both of these torques are in the same direction. So the torque of the beam is in the same direction as the torque of the person. And because it's in the same directions, we can say like directions, they're going to add together to give us a bigger torque in the same direction, okay? And if we calculate that, that's going to give us our answer of 2,205 Newton meters. And adding our direction is going to be an anti-clockwise torque. Alright, we'll go our next example. So Kevin has a mass of about 75 kilograms. He decides to stand on a 5-meter long wooden beam that has a mass of 240 kilograms. Assuming the beam, just assuming the beam is in equilibrium, calculate the torque at the support A with the direction. Alright, so we have our example 2 here. Sorry, just let me load this up real quick. Alright, so we have our support A, support B. Oh, dang it. Sorry guys, just let me back. Sorry guys, I tapped too much. Alright, so we have our example here. So Kevin has a mass of about 75 kilograms, and we're given some information according to the distance. So we're trying to calculate the torque at the support A with the direction, okay? So once again, we have to identify the torques and the direction, okay? So as you can see, we're trying to find this support A, that's the one on the left. So once again, we're going back to what I just said before. So Kevin is on the right-hand side of the support A, so therefore his torque is going to be in a clockwise direction. And remember, the center of mass for the beam is going to be in the center of the beam. And the center of the beam is also to the right of the support. So once again, there's going to be also a clockwise torque from the beam. These two torques are going to add up to produce one bigger torque, and that's going to be our torque around support A, because they're both in the same direction. And once again, it's just a matter of simple calculations, okay? Alright, so we're going to consider A as a pivot because it asks for the torque at A. So we just need to draw, just not necessarily vectors, but just like, it's like a direction, okay? So as I was saying before, Kevin will have a clockwise torque, and the center of mass of the beam will also have a clockwise torque for the support A. However, if support B was the pivot, then you'll notice that they'll actually be opposite directions. So Kevin will have anti-clockwise torque, and the center of the beam will also have an anti-clockwise torque, okay? But in terms of the support A, they're both in the clockwise direction, okay? So we're going to be using our torque equals to force times distance. And we should be able to work out our total numbers, okay? So for Kevin, it will be 75 times of the gravity, which is 9.8. And that force is multiplied by the distance, and that should give us 514.5 Newton meters. For the beam is 240 kilograms times of 9.8 meters per second downwards, and that's multiplied by the distance, which is 2.1 meters. Alright, in terms of finding the distance, okay, so you're wondering how I got this just 2.1 meters. Alright, so remember how sorry. So what was I? So okay, so in terms of how I got the 2.1 meters, it's because we have to consider the center of mass, okay? So basically, so basically trying to find the distance. It's a 5 meter long beam. So therefore, if it's at the center of the mass, then it's going to be 2.5 meters on the left and 2.5 meters on the right. So notice this very left vector is 0.4 meters. So that means from the very left of the beam to the support is 0.4 meters. So that means from the support A to the center will be just 2.5 minus the 0.4, which is sticking out after the support. So if we do 2.5 minus 0.4, we should get our answer, which is 2.1, okay? So that's the reason to have our center of mass, which is 2.5, minus the 0.4, we should get our distance from support A to center of mass, and that's 2.1 meters. So like I was saying, that gives us 4,939.2 Newton meters. And also, as I was saying before, they're in the same direction, they're both clockwise, so therefore they're going to add together and produce one larger torque. And that's going to be 5,453.7 Newton meters. And if you add the direction, which is clockwise. I have our example 2. Alright, so now Kevin moves to the other side of the pivot. Calculate the new torque at support A. Alright, so Kevin is now at the very right hand side of the beam, and there's going to be a different torque here. Alright, so the first thing to note down here is it's because Kevin has now switched sides. He is now at the left hand side of the support A, and you should notice that now he'll have anti-clockwise torque. However, the center of mass hasn't moved, and that means that the center of mass will still provide the clockwise torque. These torques are in the opposite direction, and therefore they'll try to cancel each other out, okay? So he's on the left hand side of the pivot, the torque he exerts will now be in the opposite direction. So this is opposing the clockwise torque of the bar, and they'll cancel each other out, okay? So now instead of adding them together, now we'll subtract them, okay? So basically, torque, once again, just torque is 4 times distance, and Kevin's torque would just be 0.4 meters times by the force, which is 735 newtons, and that gives us 294 newton meters, and that's actually in the anti-clockwise direction. And the bar hasn't changed because the center of mass, the position of the center of mass hasn't changed, so therefore the torque will also not change. So it's still going to be 4,939.2. Alright, so now the torque's in the opposite directions, hence, this is very similar to Fnet. So for example, I have 5 newtons to the right, and I have 3 newtons to the left. So this 3 newtons from the left will try to cancel with the 5 newtons from the right, and they'll, instead of adding them together, it's actually subtracted. So whichever one is the stronger force will come out on top, and that will be our direction. So remember I said 5 newtons to the right and 3 newtons to the left. So 5 minus 3 is 2 newtons. However, the force to the left was stronger. So now it will just be 2 newtons to the left. 2 newtons to the right. The right 5 newtons is stronger. So it's exact same thing in this case. So the clockwise torque of the bar is larger than the anti-clockwise torque of Kevin. So therefore, we're going to do the larger number subtracted by the smaller number. And once we do the larger subtracted by the smaller number, we're going to get a positive number. And this positive number will be in the same direction as the larger torque, okay? So all Kevin did was just lessen the clockwise torque, okay? So it's still going to be clockwise, but it's just going to be less torque in the clockwise direction. Alright, example 3. So Kevin now hops onto a badly designed seesaw. The seesaw is 8.4 meters long and has a mass of an X amount of kilograms. The seesaw is in equilibrium, hence calculate the mass of the seesaw. Alright, so we have our beautiful seesaw here. Sorry guys, I didn't really know how to put this all at once, so just bear with me. So okay, so we have our diagram here. And the seesaw is 8.4 meters long and has a mass of an X amount of kilograms, okay? Alright. So basically, the very important key information we need to use here is that the seesaw is in equilibrium. So immediately, the first thing that should come into your mind is that the net torque is 0 Newton meters, because the anti-clockwise torque is exactly equal to the clockwise torque. Alright, so as you can see, once again, Kevin's torque provided here is on the left of the pivot, so therefore it's going to be an anti-clockwise torque, okay? And the center of mass provided by the beam is going to be in the clockwise direction, and that's because it is to the right of the pivot point. So once again, you can see that they're in the opposite directions, so they'll try to cancel each other out. So this is the key points, okay? So just ignore what's on the left hand side for now. So whatever torque Kevin has and whatever torque this bar has, they'll cancel each other out, and after cancelling out, that's going to equal to the 0 Newton meters, okay? So basically, the torque provided by Kevin is the exact same as the torque provided by the center of mass here. Alright, so we do know the torque provided by Kevin because we know that he's 75 kilograms, and that translates to 335 newtons. And we also know that he's 1.2 meters away from the pivot. So we can instantly calculate that the torque of Kevin is 882 newton meters, and that will be in the anti-clockwise direction. The center of mass will be whatever the force of the bar is, multiplied by the distance, which is 3.8 meters. So we can write that as 3.8 times of the force that we don't know, and that will be in the clockwise direction. Because we know that they cancel out to equal 0, we can make our we can set up our equations. So we set up our equations. So 882 is equal to our 882 is equal to 3.8 times by our unknown force. And if we move the 3.8 to the other side, then we'll divide by 3.8, and that will give us our force to be 232.114 newtons. Why did I say F? I should say newtons. And it asks us for the mass of the seesaw. So what we have now is the force. We just divide by 9.8 in order to find our mass. And if we do that, we'll get our mass to be 23.68 kilograms. Alright, so the next key points, this is going to be mainly your merit and excellence level questions here. So finding the force of a support, okay? Alright, so let's say you can find this force given torques and equilibrium. So let's say we have this bar, and this person is going to be on this bar. Alright, so once again, when I say finding a force of a support, so remember at the very start of the video, I said, oh, the support A and support B, they'll each be giving the upwards forces. And the weight force of the bar and the weight force of, doesn't have to be a bar, but you know what I mean. So the weight force of the bar and the weight force of the person is going to be acting downwards. So when I say the force of a support is basically what is the numeric size of the force acting on the support A. And once again, we can calculate that given the torques and the idea of the equilibrium. So the net torque equals to 0 Newton meters. Alright, so this is our very key information. So torque equals 0 Newton meters. So clockwise torque equals to anti-clockwise torque. So let's say we want to find the support force of B. We should consider the A as the pivot and use equilibrium ideas to work out the idea. I'll explain why we use the support force of B. It might be confusing for now. The reason we use A as the pivot might be confusing for now, but I'm going to explain it in the next slide, okay? So for example 1, so Kevin stands on a 25-meter long bridge of mass 1,350 kilograms. Assuming the setup is symmetrical, find the support force at B. Alright, so I have our bar here. We have our support A and support B. We have Kevin on the right hand side. And we just put our distance in. Just bear with me for now. Alright, so we're trying to find the support force at B, okay? And in order to do that, we're going to be considering the support A as the pivot. Okay, so that's coming back to our torque net equals to 0. So using support A as the pivot, we can see that there's a lot of torques acting on the bar. Okay, so support A is the pivot. We can see that there's the we can identify torques. So when we have our clockwise torque of our bar, we have our so in the support B, that's the force of the support B is acting upwards. So it's acting upwards. So instead of it being in the downward direction, it's going to be upwards direction. So the direction of the torque of support B is going to be in the it's going to be in the anti-clockwise direction. So that's going to be an anti-clockwise torque. The center of mass is going to be a clockwise torque. And finally, Kevin's going to be providing another clockwise torque. Alright, so now you can see where we're coming at here. So now support A is the pivot point. We have our 2 clockwise torques, and that is balanced by our 1 anti-clockwise torque, which is our support B. Okay, so we know our numeric values. We can calculate the numeric values for our torque of Kevin and the numeric values for the torque of the bar. These 2 torques add together to give us our clockwise torque, and we can equate that. So we can say that torque is exactly equal to the torque of the support B. Okay. So let's say we said support B was the pivot. If we said support B was the pivot, then there'll be a problem, because support B, if we're trying to find a torque, like the force at support B, and support B is the pivot, then the force at support B is actually zero. There's no distance between the torque and support B. So therefore, I mean, the force of support B is in the exact same place as support B. So therefore, there's actually going to be no torque there. So anything multiplied by 0 is still 0. So therefore, we're going to have trouble actually finding the force at support B if the support B was the pivot. So that's why we use support A as the pivot. And as support A is the pivot, we can use the idea of equilibrium. So clockwise torque equals to anti-clockwise torque to find the force supported by the support B. Hopefully that made sense. Okay, I know that was a bit confusing, but hopefully that makes sense. Alright, so as seen, the wave forces from the bridge and given as a clockwise torque, the support force from the support offers an anti-clockwise torque. We know the bridge is in equilibrium, hence the torque net equals to 0, meaning all clockwise torques will cancel out with anti-clockwise torques. And that's where we're going to set up our equation, okay? Alright, so in this slide, we're going to be setting up an equation. So the first thing we can say is that our torque anti-clockwise is equal to our torque clockwise. And we know torque clockwise is the torque of Kevin plus the torque of the bar. And we also know that torque equals to force times distance. Alright, so our torque of the bridge can be split up into the force of the bridge multiplied by the distance of the bridge, and this is added. Okay, then that's added to the force of Kevin multiplied by the distance of Kevin, and that's actually equal to the force of the support times the distance of the support. Okay, so everything on the left hand side is a clockwise torque, and everything on the right hand side will be an anti-clockwise torque, and they're equal. So that's our equation there. So now all you have to do is plug in our numbers. Okay. So referring to our last diagram, so we can, our bridge is 1,350 kilograms multiplied by gravity, multiplied by a distance of 9.5 meters, plus of Kevin's distance, Kevin's mass, and and the gravity force, and that's going to be equal to the force of the support multiplied by the distance of the support, which is 19, and that's basically setting up our equation. And now all we have to do is plug into our calculator and solve. So the F of the support times 19 equals to 140,532 newton meters. So therefore, the force of the support is 7,396.42 newtons. And that's going to be our force of the support. Alright, so finding the support force at A, so that's the opposite support force. Right, so in this case, you can either go back and use B as the pivot point and use the exact same strategy. So identify all the torques acting at B, and you know all these torques will cancel out to be 0 Newton meters, and we can set up the equation like we just did in order to find our force at A. However, after you already found B, there's a very easy way in order to do this that does not require you to do any more torque, okay? So the very easy way, you can just say that the Fnet, so like I said, the bar is in equilibrium. And when something is in equilibrium, the Fnet will be 0 newtons. So that means that the forces acting upwards will be exactly equal to the forces acting downwards. The total forces acting downwards will be Kevin, the beam, Kevin, the beam, and Kevin and the beam. And all the forces acting upwards will be the two support forces. These two support forces acting force upwards will be the exact same as Kevin's and the bar's weight force, which is acting downwards. They will cancel each other out as they're in equilibrium. Alright, so basically the gravity force of the bridge plus the gravity force of Kevin equals to the support force of A plus support force of B. So we're just setting up our equation. We already found our support force of B, so we just plug in that number in. And we should find that our support force A would be 6,568.58 newtons. Okay, so this method is more for if you're really confident that you got the right answer for the last question. However, if you're not very confident, it's always a great idea to go back and check using both methods, okay? So you could, for example, you find the support force of B, and then you use the concept of torque again to find the support force of A, and then you use this method to check whether your upwards forces equals your downward forces, and that will be your ultimate way of knowing if you got the right answer. If everything matches up correctly, so forces up equals to forces down, and the two support forces by the beam seem logical, then chances are you have the right answer. So it's just a great idea to use like multiple methods in order to check your answer, because it is worth the time, because it's an excellence level, like normally it's an excellence level question. So it is worth the time to do it. Alright, so moving on to example 2. Sorry, I accidentally put the question on the bottom, so forgive me for that. Sorry. So Kevin has burned brine, which is 60 kilograms, on opposite sides of a plank of 5 meters and mass 80 kilograms. The following information is given. So assuming Kevin is on the edge of the plank. Alright, so we want to find the force at both supports. Alright, so just bear with me while I get this loaded up. Oh no, I went too much. Dang it. Sorry guys. That's the second time that happened. Apologize. Apologize, guys. Alright, so here we have our diagram. So you can see we have our plank here, Brian on the right hand side and Kevin on the left hand side. And we're trying to find the force as both supports, okay? So basically we're going to go about this exact same way. So we're going to be using the concept of equilibrium. So the torque net equals to 0. So once again, we're going to be making, for example, we're going to make one support the pivot. And we're going to find all the torques acting around that pivot and which direction they are in. And by using that concept, we can find the support force of the opposite pivot. Or not, of the opposite support, sorry. Alright, so let's say that the support on the left is A and the support on the right is B. Okay, so the force at A, so we need to make B the pivot point, and we're going to consider all the torques around that B. Alright, so all the torques around that B, so Kevin's going to be providing downwards. It's going to curve around, so it's going to go in the anti-clockwise direction. Our weight force of the bar. Okay, never mind. We have our support force coming from okay, so just ignore that one actually. Sorry guys, we'll make some. Oh yeah, so our support A is going to be giving going to give us the clockwise torque, and finally the weight force of the bar is going to be giving us also an anti-clockwise torque. Okay, so as you can see, these two anti-clockwise torques provided by the bar and provided by Kevin is going to be completely balanced out by the one clockwise torque which is provided by the support force. So therefore we can start to set up our equation. So oh yeah, forgot about Brian, sorry. We also have Brian, which is also going to be in the clockwise direction, okay? So Brian's going to be on the right-hand side of the pivot, and if it's on the right-hand side of the pivot, that's going to be giving us the clockwise torque. Alright, so now we have two clockwise torques and we have two anti-clockwise torques. So the torque of the support force and the torque of Brian is going to balance out the torque of Kevin and the torque of the bar. Okay, so these four torques are gonna like completely balance out and cancel out to be 0 Newton meters. So therefore, knowing this information, we can make up the equation and solve the equation. Okay, so we know that torque equals to force times distance. So we have 3 times 9.8 times of 75. That will be the torque of Kevin. That's going to be in the anti-clockwise direction. And that's added on to the torque of the bar, which is 80 times 9.8 times 0.5. They added because they're in the same direction, okay? So they're in the same direction, they add together. 60 times 9.8 times 1.1, that will be the torque of Brian. Torque of Brian, that will be in the clockwise direction. And we also know that the support force from support A will also be in the clockwise direction. So that will just be 1.2 times of F, okay? Alright, so once again, in terms of finding the distances, okay, and some people are having trouble, so this entire bar is going to be having a center of mass. Once again, it's going to be in the exact center, okay? So we know how long the bar is. How long was the bar? So we know that the bar is okay. So bar is 5 meters long, and that means that the center of mass is going to be acting down exactly the 2.5 meter mark. So there's going to be 2.5 meters to the left and 2.5 meters to the right. In terms of finding the distance between the center of mass and the support, that requires a bit of extended thinking. Okay, so 2.5 meters to the left. We know that from Kevin to support A is 1.8 meters, and therefore there's still 0.7 meters left from the support A to the center of mass. However, then we know that the distance between the two supports is 1.2 meters, so therefore if there's 0.7 meters from A to the center of mass, then from the center of mass to B, it will just be 1.2 minus of the 0.7, which will give us our 0.5. In terms of the distance for Brian, the the entire bar is 5 meters, and we're trying to find the distance from Brian to the support B. So it'll just basically be 5 minus the 1.8, 5 minus okay, so it'll be 5 minus 1.8 minus 1.2 and minus the 0.9, and that'll give us the distance in between there. Okay, so once we set up our equation, okay, we just need to rearrange and solve. So we should get our force equals to 1,625.17 newtons. Alright, so we'll look at the force at B. Okay, so look at force at B, we'll be making the opposite support force to pivot, which is A. So A will now be our pivot point, and we'll have to consider all the torques acting around A. Alright, so Kevin is still going to be providing, it's going to be on the left of the pivot, so it's still going to be providing our anti-clockwise torque. Now we have our weight force of the bar. The weight force of the bar is now on the left-hand side of the pivot, and because it's on the right-hand side of the pivot, and because the weight force is on the right-hand side of the pivot, then it's going to be acting in the clockwise direction. The support force provided by A, that's it's gonna go exact opposite. It's gonna go curve around, so it's gonna be also in the anti-clockwise direction. And finally, Brian is also going to be in the clockwise direction as he is on the right of the pivot. So once again, you're going to see these four torques, and these four torques are going to completely cancel out and give us our answer of 0 Newton meters because the bar is in equilibrium. So that means we're allowed to set up our equation and solve. So we know torque equals to force times distance. So the anti-clockwise torque equals to clockwise torque. So anti-clockwise torque would be the Kevin and the support force. Not support force, the torque at the support. And that'll just be everything on the left hand side. Everything on the right hand side will just be torque of Brian plus of the torque of the center of mass of the bar. Alright, so in terms of getting help with the distances again, so how do we find the distance between the center of mass and the support A? So once again, we'll have to use our idea of center of mass. So if there's a center of mass in the middle, there's 2.5 meters to the left and there's 2.5 meters to the right. Alright, in terms of finding the distance, we know that from Kevin, so from the very end of the bar, so from the very left-hand side of the bar to support A is 1.8 meters. And from the center of mass to the support A will just be 2.5 minus everything on the left, which is 1.8, which will be our 0.7 meters used in our equation. In terms of Brian, okay, so in Brian, we've already established that the distance from Brian to support B is 1.1 meters. All we need to do is add on the 1.2 meters in order to find the distance from Brian to support A. So we just add the distance between the two supports, and that will just be 1.1 plus of 1.2, and that will be our 2.3 meters that's used in our equation. So now we just need to solve our equation, and that should give us our force is equal to 481.83 newtons. And finally, what we can do to check our answer, I forgot to mention this in the slideshow, but a final thing we can do to check our answers is to calculate all the forces acting downwards, and then add our two answers up. Do our two answers added up equal to all the forces acting downwards? So when I say all the forces acting downwards, that's the weight force of Kevin, the weight force of the bar, and the weight force of Brian. Does that equal to the two forces upwards by the two supports? So basically, Kevin is 75 kilograms, so basically 75 times of 9.8 plus of the weight of the bar, which is 80 times 9.8 plus of 60 times 9.8, and that equal to 481.83 plus of 1625.17. So if they're equal, then you know you have the right answer for sure. Alright, so finally we have our bonus for experts. Alright, so this is a bonus, so anyone that's interested in doing the bonus can leave their answers in the comments below. First person to give me some correct answers, I'll buy them 2 Afghan cookies from the canteen. So it's worth your time, for sure. So Kevin has burnt Brian 60 kilograms, jumps into a broken bench, 8 meters with springs as a support. The springs have spring constants of 7,300 Newton meters, and the springs extend as they are on the bench. So we have our bar, and the two. I couldn't find any good images of springs, so I'm just gonna. So the circles represent the springs. Okay, it looks like a trolley, but just ignore that. So we have our A on the left hand side. We have our spring A on the left hand side, and we have our spring B on the right hand side. Alright, so we have person 1, and that's Brian. And we have person 2, which is Kevin. Alright, so the information given is that the angle theta that's made between the angle theta made between the bench and the horizontal will be 30 degrees. And we'll also give you some distances. So these distances given are the distances of the bar. They are not the distance. It's not the horizontal distance. It's the distance, the diagonal distance of the bar. Okay, keep that in mind. Alright, so 4.2 we have there. We have our distance between Brian and Kevin is 5 meters. Alright, so another information we're given. So the amount of extension on spring B is 0.272 meters. Assuming Kevin's on the edge of the bench and using equilibrium, find the mass of the bench and the extension of the spring A. So when I say Kevin's on the edge, that means it's assuming that Kevin is on the very end, as far as you can go on the right of the beam, okay? So as far right as you can go, the very edge of the beam. Alright, so as a hint for this question, okay, hint is that the torque equals to force times distance, but remember that the force and the distance need to be perpendicular to each other, okay, and that would be the hint, okay. So, torque and so force and distance need to be perpendicular, and I want you to find the mass of the bench and the extension of the spring A. If you think you have the answer, comment down below, and first person to give me 2 correct answers. In terms of working, in terms of working, okay, you don't have to show your working on the comment, but I don't want anyone to guess the answer, okay, because that's not going to work out, okay. So if you just try to work out the question by yourself, don't try to do any guessing, okay. There's a strategic way to do this question. And first person to comment down 2 correct answers. So 1 is the mass of the bench, and 2 is extension of spring A. So how you lay out your answer will just be 1 dot mass of the bench, your answer, and then bottom will just be 2 dot your answer for extension of spring A. Alright, so thank you for watching this video on torque. Hope you enjoyed, and I hope to see you all in the next one. Thank you. Bye.